Hello, my name is David Waltzman and I am a Senior Simulation Product Specialist with GoEngineer. This video is the second installment on a topic that we have previously ignored in our knowledge base. That's right, folks, I am talking about sharks. Sharks have been around for hundreds of millions of years, way beyond humans, and definitely pre-SOLIDWORKS era. Sharks predate insects, mammals, and dinosaurs. Welcome to the shark bite, an FEA approach. Once a shark acquires the location of food, the next phase of the process is to deliver a debilitating bite into its prey. Great white sharks have 5 sets of teeth, 2 of which are exposed at any given time. To study this predator's behavior in the water, humans have to come prepared. Usual methods of protection include cages and chainmail suits. Here we'll be simulating a single 3-inch tooth from a great white shark biting on a 1/4 inch of steel armor. So we start off here with an image found of a 3-inch great white shark tooth. From there, I use the sketch tools in SOLIDWORKS to create a profile that assumes that shape. I then created our 1/4 inch plate here, a 2-foot long section to analyze our bite. Now let's create our static study to simulate the bite. The first step is to create our 2D simplification. In our case here, I chose my front plane where my sketch resides and said that my tooth is a 32nd of an inch thick. Following that, it's important to define the materials that are in our simulation. So we're assuming that the tooth is made of a ceramic porcelain similar to our human teeth, and that we have alloy steel for our body armor. All these properties come in our SOLIDWORKS material library in the software. All the items in red show required properties, in blue are icing on the cake, and black are not used in this type of study. Moving our way down, I defined how the 2 bodies are in contact in our simulation. So the edge of my tooth and the top of my armor have a no penetration contact. There's not any friction defined in this case, as it shouldn't significantly affect the results. Next, we need to say how everything is held in our model. So I fixed the ends of my 2-foot section of armor so that those are held in place and it can deflect in the middle where the tooth is making contact. I would also like my tooth to come straight down on my geometry. So I selected these top edges here and I'm going to force it to not be able to move in this direction laterally. Now let's go on to the loading. Right, so when the shark's jaw is clenching down, it's going to be transmitting a pressure through the top of the teeth, and then the teeth will bite down on the plate. So I'm specifying this edge along the top here with 50 psi for now, and we have to specify a direction of it. So now we see that this pressure will be making the tooth go downwards. The final step in the FEA process is the discretization of our solids, just creating all these small triangles to characterize our geometry. Once we're done with all of that, we run our simulation, and several seconds later, we can see the max stress on our model here. So we're just viewing the results on the armor, and we can see that we have a maximum stress of 379 megapascals under our 50 psi load. The linear static study makes several assumptions when performing a calculation that make it an idealization. This scenario is more accurately depicted by a nonlinear dynamic study because as the plate deforms, a new stiffness matrix is created for each calculation step. This reduces the max stress significantly. So let's go over to our nonlinear dynamic simulation. We see while visually it doesn't look drastically different, our stress has dropped to 255 megapascals. This is a 33% reduction. So from here, let's increase the load 50% to 75 psi. If we look at our stress results, we can see that we now have a maximum stress of 344 megapascals. Furthermore, there is a 35% increase in max stress from the previous loading condition. If we had performed a linear static analysis, doubling the load condition would result in doubling the max stress. This would yield an overshoot of 120%. Finally, let's go over to a load that's 5 times that of what we started at 250 psi. The max stress in this scenario is 809 megapascals. This is still under the yield stress of the specified alloy steel by 3 orders of magnitude. The displacement over this whole 2-foot span is still less than half an inch. I don't know about you, but the next time I go swimming with great whites with full medieval body armor, I will feel a little bit safer. Thank you for tuning in. This was David Waltzman from Go Engineer.